2 o'clock, so we'll go ahead and get started. As some quick reminders before we jump in, I'm going to ask that everyone keeps their microphone muted during the talks, just so we don't get too much background noise built up. And if you have any questions during the talk, feel free to type them in the chat, and we'll make sure that we get to those. There will also be time at the end of the talk to ask questions as well. So whatever you're most comfortable with. But I'll make sure that the chat questions get answered as well. So today we're happy to welcome Sanjana Curtis, who is currently a graduate student at North Carolina State University. She's graduating soon and going to be defending and off to a postdoc, I believe. And she does a lot of work on simulating core collapse supernovae and binary. I think you're dabbling now in binary mergers as well. So take it away. Yeah. Sanjana, don't forget to unmute yourself. Yeah.
Okay. Did that do it?
Yeah, I can hear you.
Perfect. First time worked. Anyway, thank you, Mackenzie, for the introduction. Thank you, Irina. I'm excited to be here. Thank you, all of you, for coming to the talk today. What I want to talk about is core collapse supernovae and taking explosion simulations of core collapse supernovae all the way out to predictions for light curves and spectra. And the way we do this is through the explosion simulations that already exist with the push method and nucleosynthesis predictions that already exist that I worked on. And this is the piece where the project is about connecting now these simulations and the nucleosynthesis predictions to what observers can actually measure. So this work was done by quite a few people, some at NC State, some at Atlanta for the most part. On my title slide, you will see on the bottom left a picture of supernova 1987A. But to mix things up, I've put it in infrared, visible, and X-ray. And on the right, the two plots that you can see, those are our results, a little bit of a sneak preview for you already. So the way I want to do this talk is give you a very quick overview of core collapse supernovae, what they are, what the explosion mechanism looks like, motivate why we care about light curves and spectra, and then tell you how we take our calculations all the way out to these predictions of light curves, show you what we have as a result, and then summarize. So let me just kick off with what core collapse supernovae are. And these are the explosive deaths of massive stars. And by massive stars, I mean a star that's more than 8 to 10 times the mass of our sun. And so in this picture, if you look at the evolution that's happening on the left, that's for a solar mass star, and it ends up as a white dwarf, but I would like you to focus your attention to the evolution channel on the right, where a massive star evolves into a red supergiant, goes supernova, core collapse supernova, and then leaves behind a neutron star or a black hole as remnants. So this is what core collapse supernovae are. But how does this happen to a massive star? Why does it explode? And here's a very brief overview of that, because this is an active area of research and a lot of people are working on it, but I can show you a schematic, and the schematic corresponds to the neutrino-driven mechanism for core collapse supernovae. So you start with this massive star that has layers of different elements that it has fused from hydrogen to helium to carbon to oxygen, and it has a core made of iron. And this iron core, as it fuses more and more silicon, this iron core keeps growing until it becomes gravitationally unstable. And once you become gravitationally unstable, the core starts to collapse. And at some point during that collapse, the densities become very, very high, and you hit nuclear densities. And at that point, the repulsive part of the strong force kicks in, and the equation of state of the matter stiffens very suddenly. And what you have is at the center, this protoneutron star object begins to form. And then outside of that, a shock is launched, which starts going through the star and disrupting it. This is the prompt shock. And the prompt shock, after going some distance into the star, stalls because it loses a lot of energy. So this shock that comes after a bounce is not the shock that actually disrupts the star. And you need something else. You need a little bit of extra energy to get the shock to not stall and in fact blow up the star. And in the neutrino-driven mechanism, where we get this energy is from neutrinos. So your central object that's forming this protoneutron star is giving out an intense flux of neutrinos. If we can get some of the neutrinos to absorb behind the shock and reheat that material, then you can get the shock to re-energize, go through the star, get an explosion. And during this explosion, you have a lot of nuclear processes happening, explosive nucleosynthesis occurring, and as the star disrupts, it puts out all of these elements into the interstellar medium, and that's the big picture of your core collapse supernova explosion. However, this is still being studied in multi-D simulations. People are starting to get explosions. For our purposes, because we wanted to look at a lot of different stars, we have to go with something that's computationally affordable, and that's spherically symmetric simulations. The problem in spherical symmetry in simulating massive stars and core collapse is you can put in all the different pieces of physics that are relevant and interesting and still not get an explosion. There are multidimensional effects that are necessary that spherical symmetry does not capture. In a physically informed way, add extra energy to the system and induce an explosion in spherical symmetry. So that's the idea of these core collapse simulations that I'll be talking about. So why should we care about core collapse supernovae anyway? And as I just mentioned, these explosions make a lot of different elements. And so core collapse supernovae are basically element factories, and you can get things like alpha elements, ion group elements, even some heavier elements. They also give birth to neutron stars and black holes, very, very interesting objects in their own right. Because of the enormous amount of energy that you output in the explosion and the elements that you make, core collapse supernovae can affect how galaxies evolve dynamically as well as chemically. And then with the formation of the central object, the protoneutron star, you can really probe matter that's at high densities. You can probe neutrino physics. And luckily for us, core collapse supernovae are multi-messenger sources. And so you can get your light, you can get neutrinos. If you're very, very lucky, you can also get gravitational waves detected. So this is a really, really exciting topic. And we're going to focus on the light piece because it is very informative. And for a long time, we've had so many observations of core collapse supernova light curves piling up. And so we really want to understand them and see what we can glean from all of these observations. And so here I'm showing you on the right a plot of some number of observed core collapse supernovae. And it's the bolometric luminosity plotted against the time after explosion. And at once you can see that qualitatively, there are similarities in the type of light curves that you get. However, there are also differences, and the one outlier that you can immediately spot is the 1987A light curve, that's the green crosses. So while core collapse supernova light curves have qualitative similarities, this hides a diverse range of behaviors. And that diverse behavior is the key to many interesting topics, including things like what kind of nickel, how much nickel can you make in a core collapse supernova? What's the explosion energy? Which stars explode, which don't? And so there's a lot of information hidden in these light curves and in the diversity of these light curves that we want to be able to extract. And so not only can you get some, the nickel 56, you can get an estimate or a constraint on the explosion energy, you can get a handle on the progenitor properties, and people are also trying to work on this to standardize them in the same way that type 1As are standardized to measure cosmological distances. And as interesting as light curves are, spectra are more revealing. And so from spectra and how they evolve over time, we can get things like the photospheric temperature, and so the temperature and the velocity of the matter in the star, in the ejecta. By looking at line strengths, we can get the different quantities of the different elements, the composition of the star. And by looking at the line profiles, we can get information on velocities, the morphology of the ejecta, how much mixing is happening in this explosion. And so there's basically a whole list of topics where your light curves and spectra and understanding them can give us a lot of information. And it's just things related to progenitor properties, to stellar evolution, whether our models for stellar evolution make sense, what the explosion mechanism itself is, the equation of state, nucleosynthesis, of course, and then the formation of neutron stars and black holes. And so there is very good reason to be extremely interested in light curves and spectra of coronal collapse supernovae. And what we're trying to do here is explore a wide range of models and sort of see what kind of behaviors we can observe, and maybe even try to see if there are trends, say with the mass of the star or the metallicity of the star, that we can pick up on. But to do this, we do need to do a lot of simulations and take them all the way out to observations. And people have made efforts in the past to do a similar broad study. The difference between those approaches and ours is that this is the first time that people are taking, that we have taken a calculation of the explosion and then mapped it sequentially all the way out to the light curves and the spectra that you would expect. The approaches that have been used before this, it's more things like thermal bomb or piston method, where you take the progenitor star and then you have a lot of different parameters that you can fix, as opposed to the method that we're using, this push method. I'll get into that in a few minutes, where we have a parametrized method to do explosions that was calibrated, and now we're making predictions and actually simulating the entire explosion in spherical symmetry, and then computing these observable quantities starting from that simulation. And so the purpose of this is not just to compare with that observations, it's also going to tell us a little bit about whether this explosion method that we're doing in spherical symmetry, how realistic it is, whether we can get predictions that make sense, and whether we can get a handle on observational data from a method like this. And even bigger picture, in the end, this is all going to be part of the multi-messenger database that comes from the same set of models, the same set of explosion simulations. And so you've got now nucleosynthesis, explosion energy, light curves, spectra, gravitational waves, and that's going to be sort of the end goal of this big set of projects. So this part, the light curves and the spectra, we have just submitted to AppJ. You can go find the paper in the archive if you're interested. That's the link right there. And then all the data is going to be publicly available on this NCSU AstroData link. Okay. So that is the objective. And now I'm going to go ahead and tell you how we do everything. So our methods are next. This is, oh, whoops. Okay, this is the big picture, sort of a flow chart of everything going on in this project. We're going to need this as we go through the different steps. So we start with progenitor models from a stellar evolution code, and we've taken about 62 of them. And they roughly lie in the mass range 11 to 75. And there are 3 different metallicity sets that are included. So your solar, subsolar, and zero metallicity models. These progenitor models go into 1D explosion simulations done with the push method. And from these explosion simulations, we can get explosion properties and nucleosynthesis yields, both of which are relevant for the light curve. Then we take the explosion simulations and we map them to the SNEC code, which is a radiation hydrodynamics code that does diffusion, flux limited diffusion. And from SNEC, we can get bolometric light curves. And then the next step is to map it to SUPERNU. The SNEC simulation gets mapped to SUPERNU, which does Monte Carlo photon transport. And then out of SUPERNU comes your bolometric and broadband light curves, as well as spectra. So the reason there's this double mapping is twofold. One is at the end of the explosion simulation, that's roughly usually 5 to 15 seconds. The ejecta are mostly ionized, and diffusion is a good approximation at that point. And so when we map to SNEC and we do this hydrodynamical evolution of the shock breakout, and you have the diffusion, well, the shock breakout is not under the diffusion approximation, but after that, it's a good approximation to make, and you can really just simulate the light curve with SNEC, and it's pretty reliable. And then SUPERNU is necessary because SNEC can only give us, being a diffusion code, it can only really give us bolometric light curves. And so if we want spectra, we want Monte Carlo transport here. And so that's what SUPERNU does. However, it does assume that the outflow is homologous. And so that's what decides when we go from SNEC to SUPERNU. And another nice thing is that being a Monte Carlo transport code, around the time that we map from SNEC to SUPERNU is when the power of that Monte Carlo is really being harnessed, because at high optical depths, Monte Carlo does get bogged down and you need clever tricks to speed it up. So that's the big picture. Now I'll go into the different pieces individually. And so here is a look at our progenitor models. And so you've got 3 different sets: the S series, the U series, and the series. They all are single star progenitors, non-rotating. The pictures here are showing you how much of different element is the star composed of. And so on the y-axis, you have how much of hydrogen, helium, carbon, oxygen, ion. And on the x-axis is the zero-age main sequence mass of the stars in our different sets. So the top right plot is the solar metallicity set, the bottom left is the low metallicity set, and the bottom right is the zero metallicity set. And the reason I want you to see these is to notice that the degree of mass loss is very different for these different sets. And so we really do need to do different metallicities. We can't just do one and say, this is what a 30 solar mass star looks like. For the S series, the lower mass stars retain most of their, or a substantial fraction of their hydrogen, but the higher mass stars are very, very stripped. And for some of them, you don't even have helium left anymore. Whereas for the low metallicity stars, they experience very little mass loss. And so their structure at the end of their lives is pretty much very similar to how they started out. So you have these massive hydrogen envelopes, not a whole lot of mass loss going on. These models are mapped into the Agile IDSA code, which does the explosion simulations. And the details of the push method and how we do the parametrized heating to get these explosions, you can find in Perego et al. And Ebinger et al. I'll tell you a little bit about how it works. Push is inspired by the fact that multi-D simulations are beginning to see explosions through the neutrino-driven mechanism. And so the idea is that if we can get a little bit of extra neutrino heating behind the shock in the gain region where the neutrinos are heating, in spherical symmetry, we can reproduce the explosion in a physically reasonable way. And by doing this, not only can you do the whole explosion simulation, you can follow the collapse of the star, and then you can, in a self-consistent way, have predictions for mass, for the mass cut, so the neutron star mass that you would get, and the explosion energy, and the nickel-56. All of these things are consistent with each other. They're not put in by hand. So that's the power of this method, is that you can get predictions out for all of these quantities. So the idea here is, as I mentioned, the parametrized neutrino heating. is simply to take some fraction of the heavy flavor neutrinos and deposit it in the gain region to get that little bit of extra energy to get the explosion going. But it was calibrated, the parameters that are in the method, they were calibrated by comparing to supernova 87A. So once that calibration is done, we are not going to touch it anymore. If you give me a star, I will put it into push, and out comes an explosion energy and a nickel mass and a mass cut and all of these different quantities. And so here's a quick example of what the work that has already been done. So here, the 3 papers that are listed are the papers that had the explosion simulations and the nucleosynthesis predictions for the models that I showed you. And on, here in this plot, on the y-axis, you have ejected nickel-56. On the x-axis is the explosion energy. And then some observed core collapse observations have been plotted. And you see that our explosion energy and nickel are roughly in the same ballpark as most observations. So that's comforting. But now we're going to take it to the next level. The SNEC code is a Lagrangian hydrodynamics code that does diffusion. We map to SNEC from push at the end of the push simulations, right before the shock leaves the simulation domain. At this point, we have a lot of hydro information that SNEC needs, and that comes out of the Agile code. And there's also composition information that comes out from a full nuclear reaction network calculation that was done with this CFNet reaction network. SNEC can do the different relevant pieces of physics for light curves, so like radioactive heating by nickel-56, recombination of different elements. It can do everything from hydrogen, well, it can do pretty much all the elements in the composition profile, but we've chosen to cap it off at oxygen because hydrogen and helium are the ones that are usually most relevant. Oxygen only becomes relevant for the stripped envelope supernova. So all of these different pieces that light curve predictions require that physics we've added, we've chosen to simulate. There is also boxcar smoothing that's done in SNEC, and the purpose of this is to imitate the mixing of the composition that is missing in spherically symmetric simulations. We just don't have a mechanism to do mixing in 1D, and so in a hydro calculation. And so the boxcar smoothing sort of mimics how the composition profiles no longer have sharp interfaces, but instead there's mixing going on at the interfaces. The SNEC has a mechanism for inducing explosions, so the thermal bomb mechanism that I mentioned, but since we have these already exploding supernova models, we basically disable that option. And after mapping to SNEC, you can get bolometric light curves, you can get broadband light curves. The broadband ones are produced under the assumption that you're at local thermodynamic equilibrium. So they're not quite, that you have a Planck spectrum. So that's not quite correct for all the different bands, but you can still get some light curves, broadband light curves out. This is what it looks like to actually, in terms of a profile, all the things that I just said. And so here's a density as a function of mass coordinate for one of our models. The different lines are the progenitor model right before we put it into the explosion simulation. That's the solid yellow line. The solid orange line is the output of the hydrodynamical simulation. And then these are stitched together to make the input profile that you need for the SNEC code. The reason is that you'll notice the orange line only goes out to about 5 in mass coordinate. We don't have the full star in the agile simulation. And so the outer layers of the star have to be appended back on before you can simulate it further with SNEC. And this is just for the hydro. We also do the same thing for the mass fractions of different elements that we put in the composition profile. And so for example, here is just the carbon mass fraction as a function of mass coordinates, and the exact same procedure has been done to generate the input profiles. Okay, so the next step is to take the SNEC simulations and map to SUPERNU. SUPERNU does implicit Monte Carlo, and it uses the discrete diffusion Monte Carlo in regions where the optical depth is high to speed it up. It also assumes that the ejecta are homologously expanding and that local thermodynamic equilibrium is valid. A nice thing about SUPERNU is that we have line opacities, multi-group absorption opacities from hydrogen all the way up to cobalt. And so you can really actually get the spectrum out. And it handles the decay chains of nickel, iron, chromium, all of the relevant radioactive isotopes. To do the mapping from SNEC, we do have to check for the homologousness of the outflow because SUPERNU uses that to formulate the transport over a velocity grid. And so that's the condition that we will look for when we map. And out of SUPERNU comes your bolometric light curves and broadband light curves and spectra from a full Monte Carlo calculation. Okay, this is what it looks like to check homologousness. We plot the velocity as a function of radius, and we try to fit a straight line through it. And when the fit is good enough, we say that that's the point of mapping. And at that point, you take your SNEC hydro information and map that to a velocity grid. And the plot on the bottom, for example, shows density as a function of velocity and temperature as a function of velocity for our simulations at the time of mapping. Okay, that was an overview of the methods. And so if there are any questions, I can take them at this point. Otherwise, I'll continue to the results.
It doesn't seem like there are questions right now. Yeah.
Okay. All right, onwards to the results. So here are SNEC light curves, bolometric light curves for the entire S series of models. So S series being our solar metallicity models. And you can see the three different panels that are your bolometric luminosity as a function of time. The bottom left is 11 to 22 solar masses, the stars. And then the top right is your 27 to 32, and then the bottom right is 33 to 75. And so we're going from the lighter to the heavier stars as we move across these plots. And what comes through immediately is for the lower mass stars, we have what looks like a standard type 2P, P for plateau, light curve, where the luminosity is flat up until about 100 days, and then you drop to the radioactive tail of the light curve. Between 27 to 32, you can see that the behavior is starting to change, and the plots are, and the plateau lengths are getting shorter. You don't really have a plateau by the time you get to 32. And then as we move on to the even heavier stars, the very stripped stars, in fact, what comes out is no longer a type 2P light curve at all. It's in fact what a stripped envelope supernova looks like, where there is no plateau. You simply have this broad peak that's driven by the nickel heating. So the plateaus go through some sort of a transitional phase, which is hard to put them into some category. And then you have these stripped envelope supernova. So qualitatively, this makes sense because the low mass S series stars have a lot of hydrogen, whereas the stripped envelope stars simply do not. And so since the plateau is related to hydrogen recombination, that existence of that feature means that you do need hydrogen, although it's not sufficient, as you'll see. It's a necessary condition, but it's not sufficient to have hydrogen to have this plateau. Moving on to the lower metallicity models. Now we've got on the left all the subsolar metallicity models, and on the right the zero metallicity models. And here we'll see, except for U11, 12, and 13, so the lowest mass U-series models, there's not really any plateaus to be found at all. In fact, what we're seeing is something that looks more like a 1987A type light curve, where there's something of a feature until day 50, and then the light curve rises and then falls after forming a peak at around day 100. So there's 3 different qualitative behaviors that are coming out. There's your type 2Ps, the stripped envelopes, and the 1987A light curves. And so to make sense of them, we looked at a lot of different quantities which are relevant for the light curve and plotted them against each other just to see if it leads to some sort of meaningful separation in this parameter space, if the models naturally group together into different subgroups. And here what you're looking at is a plot of hydrogen envelope masses as a function of the pre-explosion radius of the progenitor star. So, and then our entire set of models has just been thrown on this plot. And the vertical line that's drawn is at about 200 solar radii. That's roughly your low limit of a red supergiant star. And then smaller, more compact stars are blue supergiants usually. And then the line at 5 is drawn by me to mark the separation where we see your transition happening from the 2Ps to the stripped envelope type supernovae. So yes, in fact, if you look at these 4 different quadrants that I've divided the plot into, you will find all of our 2P models lying in the first quadrant. So they have a lot of hydrogen and they're big. In the second quadrant are the 1987A, like most of the low metallicity and zero metallicity models. And these have a lot of hydrogen, but they're more compact in radius. In the third quadrant are the stripped envelope stars, small hydrogen envelopes or non-existent really, and they're also compact. And the fourth quadrant is these transition type light curves that we had, about 6 of them. So if we want to understand qualitatively what's the difference, the hydrogen envelope mass and the pre-explosion radius seems to be the key quantities. So we looked specifically at models to try to understand this better. It is more intuitive why a star without hydrogen will not make a plateau, but it is a little bit harder to understand why when you have a massive hydrogen envelope, you don't get the plateau feature versus a very similar star with the same hydrogen envelope mass does show a plateau. So here's 2 models, model S18, a solar metallicity model, and Z18, a zero metallicity model. The plot on the left is the bolometric luminosity, and then as a function of time. So I've also plotted the nickel decay luminosities just to see whether there's some sort of big difference in the nickel that's driving this difference in the light curves, and there's really not. The main difference between these 2 stars appears to be the radius. So your 18 solar mass star that does have a plateau is a big star. It's 1,000 solar radii, whereas the zero metallicity star that does not is only about 10 solar radii, which is more typical of blue supergiants than red supergiants. So we looked at this in more detail. And so the idea here is we're looking at how the light curve forms as a function of time in a movie. And we're also looking at the temperature profiles of the stars. Okay, there's a lot of information here, so I'm going to take a second to explain all of it before I play the movie, and then I'll play the movie again, and hopefully we can all come to an understanding of what's going on. So the plot on the left is still the plot that I showed you on the last slide. It's bolometric luminosity as a function of time. The solar metallicity model has a plateau. The zero metallicity model does not. The plots on the right will show you the temperature profiles of these 2 models. The color scheme is the same. The orange is the zero metallicity model, the blue is the solar metallicity model, and the temperature is plotted as a function of mass coordinate. There's also a lot of shading. The shading corresponds to the different elements in the composition of the star. So you've got your hydrogen in green, helium in this pink purple color. There's oxygen, the yellow, and then the nickel, which is rather important. That's in this light blue right here, more centrally located than the rest of the elements. The dotted lines, so the shading that's solid is done for the 18 solar mass star, and then the dotted lines are for the zero metallicity star. Sorry, the solar metallicity star versus the zero metallicity star. So there's not a whole lot of difference in their composition, but you can see that they will evolve very, very differently. The plot on the bottom, which is currently empty, is where the light curve will appear as our temperature profile evolves. And the x-axis will keep changing, so just keep an eye on that. The x-axis length does not stay constant. It's going to form the light curve as the movie plays. Another important thing is, once I play it, vertical lines will appear that denote where the photosphere is in the star. So the photosphere, it is basically where your most of your light is coming from. Behind that, the matter is opaque. Beyond that, it's transparent. Of course, this is all very simplified, but that's the idea of the photosphere. And it tracks the ionization, the reionization front, the recombination front in the hydrogen envelope for the most part, because ionized hydrogen is opaque. Neutral hydrogen is mostly transparent. So as the hydrogen envelope recombines, the photosphere moves in terms of mass coordinate. And that's what you're going to see. As the photosphere moves in, different regions of the star get exposed in some sense. However, what also matters is where the photosphere is in terms of radius and not just mass coordinate. So what we're going to be looking at is the mass coordinate, the temperature as a function of mass coordinate. But as the star evolves, the photosphere moves in terms of the mass coordinate, but it may be stationary in terms of the radius, depending on the fact, because of the fact that the star is also expanding. This expansion of the star, while the photosphere moves in mass coordinate, keeps the photosphere constant in radius, while the hydrogen envelope is recombining. And that's what makes the bolometric luminosity constant during the early part of the light curve. So this is what happens for the 18 solar mass star, and then you'll see a similar thing happening for the solar metallicity star. You'll see a similar thing happening for the zero metallicity star, but the plateau is not going to be as luminous because the star is small. The luminosity that you get from a more compact star is going to be at the same temperature is going to be much lower than what you'd get from a big star that's around the same temperature. Okay. Let me play this once just so you can see how things are going to change. And so your photospheres will be moving in. You are getting on the bottom the bolometric luminosity that you have corresponding to the location of that photosphere. You'll also notice that there's a kink in the temperature profile that the photosphere is roughly tracking. That's the recombination of hydrogen that's happening. And then as it moves deeper in, at some point the photosphere will start to slow down as it gets to the inner layers, where the nickel heating becomes more and more important, and not just the hydrogen recombination. So that's, and then at late times, once most of your hydrogen has recombined, both the photospheres of both stars are in the inner layers, and what you're seeing is mostly nickel heating. And the light curves begin to agree, whereas before they were rather different in terms of luminosity. So now I will play this movie again and then tell you in a little bit more detail what's going on with the two different stars that's important. Okay, back to the beginning. Whoop. Okay, So right here is the shock breakout. Your photospheres are in the outermost cell. But the photosphere for the zero metallicity star moves in very, very quickly. What this means is that the hydrogen recombination is happening very, very fast. By around day 40 or so, most of the hydrogen envelope has already recombined. It's a small star. It expands very quickly, converts all of its thermal energy into expansion, and then cools down very, very quickly. The 18 solar mass star, it took its time expanding, cooling down, hydrogen recombination happening, but eventually does catch up to the zero metallicity star. And around day 100 is when most of the hydrogen has recombined for both stars, and what we're looking at is mostly nickel, nickel heating on the radioactive tail. And then that just continues because both stars have a very similar amount of nickel at that same luminosity until whatever day we will simulate. It's probably around 200 is how far we went with this one. Okay. That was a lot. Does anybody have questions?
Hey, Sanjana, this is Panos.
Hi, Panos.
What do you mean when you say the hydrogen envelope recombine?
Okay, so as the shock wave goes through the star and shock breakout happens, your hydrogen gets ionized. And then the recombination, by recombination I mean is as the envelope cools, you get to a temperature where the electrons are now back in their neutral states rather than being excited. Does that make sense?
Yeah, thanks.
Sure. Anyone else? Okay. Well, in that case, I will continue. All right, so that was the different qualitative classes and trying to understand why the light curves look the way they do. But also very interesting is to actually try to get a handle on what kind of light curve properties show up, how the light curve properties change as you change the progenitor properties and the explosion properties. So is there some kind of trend that we can identify? And so this is preliminary work, or rather like a proof of principle thing that we've done in the paper already, is active subspace analysis. And the idea is, given our predictions for different light curve quantities, and for example, L50 that's shown on the left is the luminosity at 50 days. And then on the right is the T peak, is for the stars that, for the light curves that rise to a broad peak, how long does it take to hit the peak luminosity? These kind of quantities, how they relate to things like the zero-age main sequence mass of the star, the radius of the star, mass of the hydrogen envelope, how much nickel was made in the explosion. All of these different progenitor quantities and explosion quantities. And then you have all of these different features in the light curves that we're trying to quantify. Here we've grouped together the under broad peak, we've put both your stripped envelope supernovae and 1987A like supernovae. This work was done mainly by Noah Wolf, who is a junior at NC State, a Goldwater scholar among his long list of accomplishments. But if you're interested in the details of how exactly this was done, please check out the paper. There's a subsection and appendix and everything describing to you how this method works. The idea here is, given all of this information, to try and see if you can identify some sort of key quantity. Given all of these inputs, is there, which one of them matters the most? And what it looks like at least for this plateau luminosity, and then also for the time it takes for a light curve to hit its peak. For both of these quantities, the nickel-56 mass was emerged basically from this calculation as the most relevant quantities to decide what kind of luminosity you will get. Now I will move on from SNEC to talking about SUPERNU. And here are some, for the three different classes that I've been mentioning, 3 different models from those classes. And so on the left is bolometric luminosity as a function of time. The light curve in black is the SUPERNU light curve. The dotted is the prediction that we had from SNEC. This is the solar metallicity 18 solar mass star. That is your typical type 2p supernova. On the right is a 36 solar mass solar metallicity star. That's your stripped envelope supernova. Again, your SUPERNU and SNEC light curves. And on the bottom is a subsolar metallicity model that looks more 87A-like. And there are a few things going on here. Yes?
Sorry, you have about 5 minutes left.
Oh, okay. I will hurry. There are a few things going on, but the important thing is, even though the predictions are quantitatively different, which you would expect from these 2 different codes, qualitatively, the classes of these light curves are similar. And so that's comforting to know that you do not see qualitative changes in the behavior. The good thing about SUPERNU is now we can also have these broadband light curves. And so, for example, not only do you have for this S18 model on the left is your usual bolometric luminosity, on the right, we've plotted the UBVRI light curves. And you do see a very quick decline in the U and B band magnitudes that is also observed, which a code that does gray diffusion cannot give you. There is a bump feature at the end of the light curve. I can go into that if people are interested, but this is a well-known issue with 1D models because of the lack of mixing, that you do end up finding this artifact feature in the light curves. And then also from SUPERNU, we have Spectra. Now, this is, again, an 18 solar mass solar metallicity star, still the absolute magnitudes from the last slide plotted on the left, but now I'm also showing you the spectra. And the reason is that it's, you can understand why the U and the B bands decline so quickly just by looking at the spectrum. At short wavelengths, there's a lot of ion line blanketing going on. And so, for example, as you go from 20 to 80 days, you'll see that the flux, not only does the general continuum decay, also especially at the low wavelengths, the flux is dropping very, very quickly. And so by low or short wavelengths, I mean under 4,000 angstrom. And so all this flux is already gone by day 80. And that's what you're seeing in the magnitudes happening at these short wavelength bands. That's what you're seeing in the spectrum occurring also. So that makes sense in terms of the consistency of these things. And then also the spectra for the 3 different classes of models. And well, you can see that they do not look the same as they should. They should be different. The difference between the 18 and the 36 solar metallicity model is simply related to the stripping. You're seeing for the S36 a spectrum that is rather typical of what a stripped envelope supernova looks like. These big broad features are related to oxygen and calcium and things like that. For between the S18 and the U18, the main difference is for the low metallicity models, the flux decay at short wavelengths doesn't happen quite as quickly. They just don't have that much metal content, and so the blanketing is not quite as dramatically visible as it is for a solar metallicity model, for example. So
should wrap up.
Here I've shown you.
Oh, perfect.
Sorry.
No.
Yeah.
We just
So I've shown you basically 3 models for SUPERNU in more detail, but we have light curves, we have spectra for all the 62 core collapse supernovae that were simulated, taking for the first time a spherically symmetric parametrized simulation like this, all the way out to predictions that you can measure, you can compare to. There's going to be a whole database online that is open to everybody that you can go check. If you want more information, more detail about anything, please do not hesitate to contact me. My email and my Twitter are both on the slide. Here in this work, we showed you how different qualitative classes emerge in these 62 supernova simulations. There's also a beginning of an active subspace analysis of the different light curve properties as a function of the progenitor and explosion properties. And this is all going to be part of a bigger multi-messenger database from this set of models. And there is real power in this method because now we have a pipeline that goes all the way from your explosion to observables. And basically, we can expand it to include different models. We can expand it to include different stellar evolution progenitors that we're getting. And of course, eventually, ideally, you would also extend this to multidimensional simulations and really try to get a handle on how well we understand the physics of core collapse supernovae. So that's where I'll stop. Thank you very much for your attention.
Thank you for the great talk.
Take questions.
So we'll have some time for questions. There will be an announcement from Irina at the end with some sort of future updates. So if everyone could stick around for that as well, that would be great. But if anyone has questions, feel free to jump in or type in the chat and we'll get those answered.
Okay, I have 2 questions.
Yes.
So PUSH was tuned to observations of 1987A. Do you think that this has any effect on observables from non-87A-like progenitors?
Yes, that's a great question. So in some sense, yes. Okay, so if you're using a parametrized method and you've fixed your parameter to be some particular number based on one supernova, that will affect the predictions that you get. But that's kind of the point of a lot of this work, is to see, we have, by taking the 1987A parametrization, we've already made predictions for explosion energies and nickel. And then those predictions we compared to a big set of supernova, and they turned out to be consistent. So if you're asking, is there uncertainty in the method? Yes, there is some uncertainty in the method. But if we can get the nickel and the explosion energy to match up, and now with these light curves and spectra, if we can get those to match up also, well, then that tells us that that parametrization makes sense. Does that answer your question?
Yeah. And then from the subspace analysis stuff, I remember the original SNEC work, they looked at some varying nickel masses and didn't see a super strong relationship between like the plateau features and the nickel mass. I'm wondering if you had any thoughts on like what the differences were with these results, if it has to do with like the different metallicities or.
Yeah, so that's a little bit trickier. I suppose one could do that same analysis on the SNEC results and check. But one thing that's completely different is, you also have the nickel masses are varying, but we're also looking at a whole range of models. Whereas I imagine for SNEC what they did, and the nickel masses are these predictions that we have from PUSH that we're not touching at all. But for SNEC, what they did was, for the same model, change the nickel and the degree of mixing of the nickel.
Right.
So it's a different question in some sense that we're answering, but it would be interesting to look a bit more at some model or a range of results from SNEC and then a range of results from us, and whether that tells us something different. Mm-hmm. But here we do seem to find the nickel 56 comes out on top of all the other parameters in the analysis.
All right, Hendrik, I think you have your hand up.
Yeah, I had a question. Yeah, thank you for the nice talk. It was very interesting, even for a nuclear physicist. I just had a question. The progenitor models, I think, have uncertainties, for example, also from the nuclear physics.
Yes.
How does that propagate into the light curves?
That's a great and very difficult question to answer. So I think it does matter. It very much matters what the progenitor models look like. And you know, if somebody has a different set of progenitors that we could run through push, that would be honestly the best way to get a handle on how different can you know, a light curve for an 18 solar mass star look based on progenitor modeling. But here, we're pretty much taking the progenitors as a given. But if in a stellar evolution calculation, they have a completely different degree of stripping or something like that, then we would get not just quantitative, but qualitatively very different results for the light curves and spectra.
Okay, and there's a question in the chat. There are quite a few 2D models of SN 1987A. How do your results compare with those?
So that would be interesting too, if I can get my hands on a light curve or spectrum, or the spectra. In terms of your explosion energies and things like that. So our 1980s, okay, there's another caveat there. So our 1987A model calibration was a red supergiant star. And we know that 87A was a blue supergiant, came from a blue supergiant progenitor. And so when we do this light curve calculation for our 87A model, we get a type 2P rather than an 87A like light curve. So sort of we could start comparing to the 2D predictions, but we already know that the 2P light curve is not realistic. Does that make sense?
I have a question. Can you hear me?
Yes, please go ahead.
So another question regarding uncertainties. So there are uncertainties regarding the nuclear reactions that produce nickel-56 and many other isotopes, but nickel-56 is the focus of your work here. So I wonder, is there anything in your results that suggest corrections to these nuclear reactions?
That would be a very interesting exploration. We have not done that type of analysis yet. However, one could conceivably see what sort of range we get for the tail luminosities from our calculations for the light curves, and then what is observed. And if those are dramatically different, that tells us there's something going on with the nickel-56, but then I'm not sure how one would propagate that all the way back to a reaction rate. The nickel-56, it depends on your explosion energy and a lot of different things. And so I can see taking it back to our calibration of the method, or stellar evolution maybe even, but I'm not quite sure how to go you know, further back.
Thanks.
Thank you.
All right, we're nearing 3 o'clock, so I think we'll let Irina make an announcement, and then maybe we can follow up with more question and answer after that, if there's still interest. So Anna, did you want to take it away?
Hendrik.
Yeah.
Hendrik, okay.
Can I share my screen? Yes. So the first thing I want to do is I want to thank Mackenzie for the wonderful job he did. I think we had a really great seminar series. I know it's a lot of work. Especially got to produce a seminar, and there's a slot. So thank you so much. I thought it was amazing, and we really appreciate it, and I hope it was a good experience. And let's give him a hand. I have a hard time finding the hand button, but if you do, actually, I don't think I have it when I share my screen. I'll do this. Thank you so much.
It really was a lot of fun to organize. Yeah.
That's good. Yeah. No, and we all enjoyed it. Okay. Now, one indicator that tells you that you did a truly amazing job is that we had to replace you with an entire committee. So the next year will be organized by a committee of postdocs from the ARENA network, and the chair will be Panos. And I think he's around somewhere on the call, maybe.
Yes, I'm here.
Hi. Very good, very good, yes. So the idea is that we have 6 networks in ARENA, and so we have postdocs from each of the partner networks, and we'll just see how that goes. We just like to explore new things, and I think this could be really good. One idea here is that if you have these different networks, they have sometimes quite different topical foci, so you can get some diversity and some broader range of ideas and presentations, and also we hope that the group itself finds itself to be an interesting group to talk to each other, and maybe not just about seminars. And I also would like to encourage the new committee to really, you know, it's your seminar, and you have a lot of freedom. Don't be shy, think out of the box. The only thing that counts in the end is that it has to be a program that's interesting for the ARENA JINA community. But, you know, that's a pretty broad envelope. So, yeah, so I hope you will have fun with this. And I think maybe there's some people from the committee here. We could maybe go around really quick and just say hi, so we can see the faces. If this would be kind of a real meeting, you could stand up and we would see you, but we can't do that, unfortunately. So Panos, you're
Yes.
there, right?
Yes, I guess I could start. Yes.
Yeah.
Hi, everyone. I'm Panos, and I'll be the host of the ARENA seminars for the next year. I hope we will have a nice and interesting schedule for the upcoming seminars. We'll try our best.
Okay. Are there other committee members here?
Thanasis?
Yeah. Hey everyone. Yeah, my name's Thanasis. I'm a postdoc at TU Darmstadt right now. So I did my PhD at McMaster, so that's fine. And I'll be the representative of NewGrid. Yeah, I hope it will be a great experience and learn lots, meet new people, and network.
Very good. Tirani, are you there? Manzi? I think I saw Nobuya.
Yes. Hello.
Are there in the middle of the night?
Yeah.
Yep.
So actually, yeah, I'm
Yeah.
Nobuya Nishimura, studying nucleosynthesis from theoretical point of view. So actually, I'm interested in some stellar models involved in the R process and other explosive nucleosynthesis, and also some relevant nuclear physics stuff. So actually some time difference between the US and Japan, Asia is a bit, regular time is a bit difficult to join every time, but I want to contribute organizing and I'll try to attend.
You're welcome as a committee, you know, you're now in charge. If you think there's a better time,
maybe, yeah, some
no, that's something to think about, because Friday, late on Friday is also pretty bad in Germany. I know that everybody has other things to do.
Yeah, so it depends on the speaker, the place of speaker. So actually, it's good to encourage to attend from Japan or Asia. Thank you.
SNEC?
Okay.
Not, and Yunhan? Also not. Okay, well, we got to know some of the new committee members. So good luck, Panos.
Thank you.
And thank you again, Mackenzie. And I'll see you all over the next year at exciting arena seminars.
In 2 weeks.
Yeah, in 2 weeks.
Yeah.
Thank you, everyone.
Okay.
Thank you very much.
Have a great weekend. And thanks, Sanjana, again. It was a very nice talk.
Thank you.
Bye.
Bye.